Okay, welcome back to the next video. Today we're just going to finish off Unit 15. So if you have not watched all of the previous Unit 15 videos, of course you probably should. So today we're going to finish Unit 15, and the last unit that we're going to talk about right now is chemical equilibrium. Chemical equilibrium. Okay. So based on chemical equilibrium, if we were to kind of, you know, play a little thought game right now, we can imagine that most chemical reactions, right? We can say most chemical reactions are reversible. They might not be directly reversible, like if we took carbon and reacted it with oxygen to form CO2. We wouldn't say that this is a reversible reaction, right? We won't say that this is reversible because the product is highly favored. So since it's highly favored, we say it's basically a one-way reaction. But actually, reversibility is determined by our delta G value, by our Gibbs free energy. And this energy is what determines what reactions will be reversible and which ones won't be reversible. It depends on how spontaneous it is, which means that depends on our delta H values as well as our delta S values as well as temperature. So it depends on multiple different factors. This reversibility depends on delta H, delta S, and delta T. So it depends on specific conditions of the reaction, and also, how much heat is liberated by the reaction, how much additional disorder is liberated by the reaction. So we can control the temperature, but this is kind of, depends on the chemical reaction that we're observing. So if we can imagine, right, this is, oops, I don't know what's going on with my eraser right now. There we go. Okay, so if we can imagine this is reversible, but we don't write it as reversible because the products are so highly favored that this reaction isn't going to reverse itself under typical conditions. So that's why we write it as being a forward reaction. So if we were to look at, a graph of most chemical reactions, right? If we were to look at the energy graph of chemical reactions, and we could have our Gibbs energy on the side, and here we can have reactant, and here we can have our products. So if you're following along in your book, this is on page 372. So what all chemical reactions do is, like I said, they depend on our Gibbs free energy. And remember, our Gibbs free energy, delta G equals delta H minus T delta S. So our Gibbs free energy depends on two different things. It depends on delta S, like if we wanted it to be spontaneous, right? If we wanted the reaction to preferably go towards the product side. So our delta G depends on our delta H, which we know we want to be negative. We want this to be exothermic. And we want our delta S to be positive, which means that the disorder in the universe is increasing. Disorder is increasing. So we need these two things to come together. And it depends, right? We can have a value, our delta G value is a small delta G value, negative 1 kilojoule per mole, or we can have it be a very, very large delta G value, negative, we just make up a value 500 kilojoules per mole. So we can have a very, very small delta G value or a large delta G value. But it depends on where this delta G value meets a minimum. Just because, as we said up here, right, all reactions are reversible, But it depends, right? If this delta G value, if we were just to plot against delta G, so delta G, from our reactants, let's say this is an exothermic reaction, and let's say that delta G is negative, and we always want delta G to be negative because that means that the disorder in the universe is increasing and the energy, the heat energy, the energy of the system is decreasing. So if we were to look at our Gibbs free energy, while a reaction is proceeding, it decreases, and then wherever it hits a minimum, this is where the equilibrium lies. And we'll see this more in chapter 17 where we deal with the equilibrium constant. This will start to make a lot more sense, don't worry about that. But this is where the equilibrium lies. So it just shows that, if this delta G value is the most negative, it looks like it's right in the center. It looks like it's 50% products and 50% reactants. But if this delta G value reaches a minimum very, very far over to the product side, right? We wouldn't necessarily consider this to be reversible because it's, in order to reverse it, we would need to input heat and energy in order to force this to go backwards to the reactant side. Typically, right, it's very, very comfortable being down here. And that's why the reaction isn't reversible, because it's difficult to reverse this reaction. But if that minimum is right here in the center, then we could start to deal with the conditions. That's why when we do equilibrium, right, our equilibrium constant, we can change that by changing the temperature of the system, by pushing the reaction forward or by pushing the reaction back. We can pump in more gas, we pump in more reactants, and then it slides back to the products, or slides to the products. We pump in more products right here, and it'll slide back down to help a few reactants, to make a few more reactants. So the whole point of this video is just to show that typically, right, chemical reactions, we can say that all of them are at equilibrium. Every chemical reaction is at equilibrium, but it's where that equilibrium lies that tells us whether we draw it as being reversible or as being irreversible. If it lies extremely far, if the minimum Gibbs free energy lies extremely close to either the product or the reactant side, it means that we can consider this reaction to be one way. If it favors 99.99% of the product, we really don't care about the 0.01% of the reactant, because we've got what we want out of the reaction. So the point of this video is just to say that reactions are reversible. How reversible depends on the Gibbs free energy and where the Gibbs free energy meets a minimum. And we'll just say one last thing. So if we were to look at one more graph, right? Let's do something like this. So what occurs here, right? If we were to take our reactants, and let's say we have a reversible reaction like N2 plus H2 reversible to form NH3. So if we have a reversible reaction here, if we put these into a reaction chamber, and we have the proper temperature in order to force the reaction to go ahead and go forward, what occurs is that, right, we have a high amount of reactants at the start. Then our reactants are decreasing. This is our percentage scale on the bottom of reactants to products. So it starts to decrease, forming more and more products. And wherever it meets the base is where it's the happiest. Because here, right, our Gibbs free energy is increasing. And by increasing, delta G is becoming more positive And more positive means non-spontaneous. And non-spontaneous means that it's not favored. So it's a reaction that does not want to proceed that way. So maybe when it hits this point, right, now order is going up. Maybe delta S is decreasing after this point. Maybe it's, the system's starting to become too ordered and nature doesn't want it to become ordered. So it comes back down to equilibrium. Where it's at this ratio right here, we can say it's at 65% or so. So it's 65% products and 35% reactants. So that's basically the whole video for today. I'm going to start answering these questions in the end of the chapter. There's only 7 of them, so expect some more videos coming soon.